So now I'm in section 2.2. This is page 86 inside of your textbook. If you have a different edition, it's going to be a different number. But what we're looking at now is we're looking at this question of investigate the limit as x approaches 0 of sine of pi over x. Okay? And so we've got a new example. We've already looked at the first three examples and asked ourselves, okay, well, what does this have to do with this intuitive notion of a limit, right? And now I've got a new example, and what new is this bringing to the table? What new information is it going to bring to the table? How is this going to help me think deeper about limits? Okay, so I've got this limit, and the first thing that I'm going to notice, I'm going to say, okay, so let's make sure that I understand what the notation is saying. So on the x-axis, that's this thing right here, as x approaches 0, right, what happens to sine of pi over x? Okay, so that's what I'm thinking to myself. I'm like, okay, well, I want to know what's going to happen there, right? How do I think about this? So he now says, okay, solution. All right, great. You're going to tell me. Again, the function f of x equals sine pi over x is undefined at 0. All right, I can definitely see that at 0, we have pi over 0. That's undefined. Evaluating the function for some small values of x. So why do that? Well, in previous sections, right, what he did was when we started to look at, values as they approached whatever this a number was, 0 here, right, he said, okay, well, what happens as we get close to 0? So that's when we get values that are small, right? Small meaning close to 0. Okay, well, we got f of 1 is sine of pi, that equals 0. F of 1/2, that's sine of pi, 2 pi, that's also 0. F of 1/3, that's sine of 3 pi, that's also equal to 0. F of 1/2, sine of 4 pi equals to 0. Okay, got it. So like I'm looking here and I'm seeing, okay, or 1/3, this is 1/4, excuse me. It's a little hard to see. It's 1/3, 1/4. Right, so now I'm getting closer, 0.1. Okay, great. That's sine of 10 pi, that's still 0. Okay, and if I'm not automatically getting like, well, why is sine of 1/2, sine of, or f of 1/2 equal to sine 2 pi? I might do something like this. I might say, okay, so sine of pi divided by 1/2. Oh, okay, got it. So that's sine of 2 pi. I can see that now, right? And that's equal to 0. I'm like, okay, got it. Sine of 0.01, that's 100 pi, right? Okay, sine of, right, pi over 0.01, okay? And that's, like you said, 100 pi, and that equals 0. Similarly, right, if you get 0.0001, and then we get even closer, like we've been doing, 0.0001, it still equals 0. So that might lead you to believe, you know what, the sine, okay, on the basis of this information, he says, we might be tempted to guess, right, that this limit is equal to 0. All right? Now, if somebody says we might be tempted to guess, it probably means it's not 0. All right? But he's going to tell you this. But this time our guess is wrong. Okay, so now I'm saying to myself, well, why is the guess wrong? What am I not seeing here? So note that although f of 1 over n equals sine n pi equals 0 for any integer n, it is also true that f of x equals 1 for any infinitely many values of x. Huh. All right, well, is that true? And he says such as 2/5 or 2 over 101. Well, let's actually, I'm going to put over in a little side note here. And you might be doing this as you're, kind of like you got a piece of paper. You might want to write some notes, maybe try out some of the examples. So I'm going to try that out. I'm going to say, okay, sine of pi divided by 2/5, this equals sine of 5 pi over 2, and that in fact is equal to 1. Oh, wow. Okay. So uh, sine of pi over 2/5, or f of 2/5, is actually equal to 1. And then he says 2 divided by 101. Well, I get it, right? It's going to say, right, it's also going to be equal to 1. So we've got a lot of those values too. And he's like, well, there are infinitely many of them. Really? Well, why is that? You might want to ask yourself, well, why is that the case? Okay. You can see that from this graph of f shown in figure 7. All right, and so what he's showing here, now what I see is that when x, so this is an x value, and this is an x value over here, okay? So when x is -1, we've got it 0, and that makes sense. Pi over -1 is negative pi. Sine of negative pi, that's 0, right? But then it goes up to 1, just like its sine graph, right? And then what he's saying is he's like, oh, look at this. Well, as I get close, right, I'm starting to wiggle here, right? I'm starting to get this big oscillation. That's what that's called. And I look at that and I go, oh, okay, all right. Now, I've studied a lot of limits. I know exactly what the issue is here, okay? But what we want to get right now as I'm reading this is that, yes, in fact, not only do we have an infinite number of ones where it's going to equal 0, right, as we get close to 0, as x gets close to 0, it's also going to have an infinitely high number of them that go to 1, okay? So I'm like, okay, I can kind of get that, right? It makes sense. So what? What's the big deal here, okay? So it's clearly not 0. And it's also not 1 because I've also got it equaling to 1, right? So now the dashed lines near the y-axis indicate that the values of sine pi over x oscillate between 1 and negative 1. Now I use the word oscillate, he used the word oscillate. You need to know what the word oscillate means, all right? So if you're sitting there going, oh, what does oscillate mean, right? Tell you, you might have to look it up. And what it means to oscillate, it means to do one of these things. That's what it means to oscillate. It means to move up and down, all right? Very important, super important in math to know what it means to oscillate. Between 1 and negative 1 infinitely often as x approaches 0. Okay, so notice infinitely often, so meaning that it like spins up and down. So I might even go back and I'll look at it and I'll go, okay, well, oh, okay, I kind of see it, right? Like as I get closer to 0, it looks like, you know, that these oscillations are speeding up. All right, that makes sense. Okay, since the values of f of x do not approach a fixed number as x approaches 0, excuse me, the limit as x approaches 0 of sine of pi over x does not exist. Okay, now, this word since, that means because, right? Or as a result of. Anytime I read that mathematically, that's a really important word, okay? What that means is that gives me the reason. The reason for sine limit as x approaches 0 of sine of pi over x does not exist is because the values of f of x do not approach a fixed number as x approaches 0. Huh. Okay. So now I'm thinking to myself, well, what's different here? What's different from the previous examples is we don't actually have an answer, right? He said that the limit here does not exist. It's a non-existent limit. And he told me the reason why that's the case. The reason that's the case is because the values of f of x do not approach a fixed number as x approaches 0. Okay, so I might write that down, right? Okay, I might like imagine that I have my paper and I say, well, if the values of f of x do not approach a fixed number, then the limit as x approaches, in this case 0, does not exist. Or we can actually, why don't we just put limit? The limit does not exist as x approaches, in this case, 0. So that's great. So if you ask me the question of like, why is it that the limit doesn't exist? One of the answers might be, oh, well, it doesn't actually approach a fixed number, right? I can't tell, in other words, what value that x is approaching. Okay? Some key points there. All right? And notice I only wrote down maybe like a couple of things. Okay? But what I did was I utilized this in order to help me understand what this statement that I just wrote meant. If the values of f of x do not approach a fixed number, then the limit does not exist as x approaches 0. Perfect. Got it. Moving on. Example 5. Find the limit as x approaches 0 of x cubed plus cosine 5x over 10,000. Huh. Okay. Got it. Right? And let's imagine that I throw in a 0 in there. Okay. Right? Well, I look at this and I go, okay, well, that's kind of interesting. Let me see. As before, we construct a table of values. From the first table in the margin, it appears, right? Okay, so if I look over here, right, this margin right over here, I get right? Notice the first table, so I'm going to go look at it. I see, well, at 1, I have 1 point, this number right here, okay? At 0.5, I have 0.124920. At 0.1, I have 0.001088, okay? At 0.05, I now get down to 0.000222, okay? And now I should be thinking to myself, well, they're getting smaller and smaller. As my x's approach 0, the values for f of x are getting smaller. Maybe it's approaching 0, right? I'm like, oh, okay, 0.01. All right. That's 0.000101. That's what I get when I put in 0.01. All right, looks like it's approaching 0. But if we persevere, whatever. If you continue with smaller values of x, the second table suggests that, right, now even smaller values of x than this 0.01. So we're getting smaller. The second table suggests that, and I look over here, and now what I see is that no, it's not actually going to 0, right? That 1 is sticking around. So at 0.005 for x, I get 0.000, I get 0.000100009 for x cubed plus cosine 5x over 1,000. And for 0.001, I get 0.0001000 again for my f of x. Well, it doesn't look actually that it's disappearing, right? It looks like that the 1 is sticking around, okay? So what I've got now is the limit as x approaches 0 of x cubed plus cosine 5x over 10,000. It looks like it's getting closer to 0.000100, and that equals 1 over 10,000. Later, we will see that the limit as x approaches 0 of cosine 5x equals 1. Then it follows that the limit is 0.0001. All right, so we'll look at that. So in this case, it's not it does not exist. It's one that just where we have to maybe inspect a little bit more closely, right? It looks like it's going down to 0, right? It looks like it. It is going to 0. But sometimes we have to more closely inspect, and on closer inspection, what we see is that it's actually approaching a different number. Okay. Now I've got a little part here. Examples 4 and 5 illustrate some of the pitfalls in guessing the value of a limit. Got it. Okay. Right. So we don't necessarily want to guess the value of a limit because it's possible that we might have the limit not exist, right? Or that we just don't take enough values, right? Okay, like that's the second part for example number 5. I didn't get small enough, right? Okay, it is easy to guess the wrong value if we use inappropriate values of x, but it is difficult to know when to stop calculating values. And as the discussion after example 2 shows, sometimes calculators and computers give the wrong values. Oh, that's a foreshadowing, right? That's like kind of like a really important part here. Sometimes calculators and computers give wrong values. In the next section, however, we will develop foolproof methods for calculating limits. Good, cool. Okay, so both of these, example 4 and example 5, according to our author, said that this is about understanding the pitfalls as you guess the value of a limit. Okay, and we have to think about like, why is that a problem? Why are each one of them a problem? Okay, one of the values of doing the reading here. But in addition, we also saw how do I know when the value, in fact, when the limit does not exist? I've got another little piece here that kind of helps me to understand what it is to actually have a limit, right? Okay, it's got to approach a particular value or a particular number. So this kind of illustrates and demonstrates the reading of a set of examples, right? Like, and notice we spent a solid amount of time. We read through each and every piece of what the author gave us tables, gave us some graphs that we went back and took a look at, okay? And we kind of dug into the language that he uses. Math is very, very precise in its language, okay? And so consequently, we want to get very precise inside of how we, right, express or understand what it is that we're reading, okay? All right, so this completes this video.